Hello everyone. Just as a warning, I am not a physicist. I just study this for a hobby. I wish I could go to a college, but it's not only very expensive, but it's kind of crappy, and it's kind of sad that that's this way things are, and I've been told there's no careers in physics, so just a warning, I only study physics for fun, sadly. So the question is very simple. Why are dipolar antennas half a wavelength? I haven't gotten a great intuitive answer to this question, so I'm gonna start. Firstly, you have to understand what standing waves are, and very importantly, the difference between longitudinal and transversal waves. Think of longitudinal as a wave that travels through a spring. In order to oscillate it, you push the spring back and forth, and the compression kind of travels through this way. Think of transversal waves as a rope. In order to transfer the energy through a rope, you have to move it up and down. This way you get a kind of even transfer of energy through the rope. One thing you might have noticed, which is probably where the 90 degrees right hand rule from electromagnetism comes from, is this. In order to move this wave right, when you move your hands up and down, the wave travels to the right in perpendicular. I keep pronouncing these words very funny, I'm sorry. Up and down relative to this direction, so perpendicular. That's very important. Another thing to understand is modes of standing wave and what the standing waves are. If you just jiggle something rope randomly, it's gonna go up and down, and then it's gonna just reflect back, and then it's just gonna, stop. I don't know why my mouth isn't working. You get the point. And in order to create this wave that does like sustain itself, like the reflections actually help it, so they stay in the system in a way, you need to make sure the frequency is the right frequency. And the formula for that, I don't remember off the top of my head, has to do with a lot of variables like the tension of the rope, the size, and the forces, but you get the point. For a lot of things, you usually hear the formula that's like, one wavelength. Sorry, this is a Y. This is usually wavelength, I think, that you see the symbols like a reverse Y. But anyway, we're gonna just talk about the first mode of standing waves, which is the frequency. And also, sorry, I should mention, there's very important if the ends are held or not held. It changes the standing waves and their looks. Is this. You move this up and down, and you put the force at exactly the right frequency. It will oscillate up, down, up and down, up and down until it stops. This is, think of it as almost like a guitar string in a way. It's a little different, but I'm just going to simplify. You know how when you pluck a string, it always makes the same note. It does, change a little bit until it reaches that a little bit, but you get the gist. This is the frequency that I'd like to say this substance or whatever you're doing likes to oscillate at. It becomes very self-sustaining, so it doesn't cancel out immediately. So it just keeps on going until you stop it. This is mode 1. There's also different modes. I'm just going to draw it like this. I think this was mode 2, where the wave is almost like one phase of the complete wavelength you get. This is mode 2. You have to increase the frequency, so it can actually, this is, anything in between will probably collapse or look weird. But once you reach the right frequency again, it will look like this. And it keeps going on until you reach mode 2, 3, 4, and so forth. Anyway, I want to get into the wavelength, and this mode specifically we're going to talk about is the rope is like half, I keep drawing Y's, is like half a wavelength, right? It's almost, you can almost think of it as you're only seeing half of a wavelength, right? If this is a complete wavelength, if you cut it in half, you're only seeing half of the wavelength, so it's half a wavelength. And the thing that's crucial to remember is that if you have the rope here, how is the wave going to complete or stand on its own? It cannot contain that wave, so there's just no way for it to, if you don't get the full portion of the wave, there's just not enough space for the wave in a sense to complete or oscillate. So the resonant frequency becomes smaller and the peak has to be here again. You get what I'm saying? So it cannot be physically smaller, because how on earth is the oscillation going to resonate and contain itself and become a standing wave? So you're probably starting to get why this is relation. There's a relation between the wavelength and the antenna size, not just any arbitrary number. However, why is it half specifically? Why not 1? Why not 2? Why not 1/4? And I should mention this is specific to dipolar antennas. They're very different types of antennas. So the reason is very simple, and it might look like this is what a mode 1 standing wave looks like, right? If you draw it here, you might get confused. The peak is in the middle. You need the oscillation at both ends. You need this to be negative, this to be positive, and then switch to negative and positive. How's that going to happen? Well, the key here is these two. What you see here is a standing wave of a transversal type. However, if you model this as like the pressure in a sense in the system, because this is not actually what it looks like physically, we're just drawing a graph. This is kind of actually what the rope physically looks like. So this is like a dimensional graph. This is energy. Like this portion is time and this is energy. The standing wave actually looks like this, which is starting to click, right? That's the key difference. This is the magnetic portion of the wave. However, the electrical current the magnetic portion causes, if it goes up, looks like this as a standing wave. The same standing waves draws this kind of graph as a current, which means this end, you can think of it maybe as positive. I'm just making this stuff up. It's a kind of a stupid oversimplification, but it helps make it intuitive. As you can see, a magnetic wave going up and down like this is standing wave creates this shape as a result, because this is not the electrical field, this is the magnetic field, magnetic portion of the electromagnetic field. When you think of it almost this way, again, this is a stupid oversimplification. When you draw a magnet up and down in front of this in the specific frequency, it moves the electrons in the 90 degrees perpendicular to it, right, and this way. And the standing wave needs to be half a length because the mode 1 is like this. And if you get different modes, you probably want to have a really nice distribution because you don't want these two to cancel out. If it's like, think of it almost this way, again, these are simplifications. If it looked like this instead, and this was the peak, this was the peak, you realize that these two kind of cancel each other out. It's not like it's going to explode, but A, it won't resonate, which means you won't really like it in a weird sense. And it will also just be less powerful and less clear as a signal. There's also another trap that I want to just mention here, which is that a lot of dipolar antennas aren't actually half a wavelength. Well, the reason behind this is that with some wizardry, you can think of it as almost like the inductance, all the properties of the antenna. It can appear, and I'm doing finger quotes a lot because these are kind of stupid forms, like words to use for this, but they can appear magnetically or electrically longer than they are. So this antenna looks, this length of the actual copper might be a little bit lower, but the actual electrical length of it, in a sense, is effective length, is what people call it, I think, is longer. Think of it as almost like a coil. The coil might be this size, but the magnetic field kind of goes up, right? And I forgot there's a term for this, but they specifically create fields, make it in such a way that fields here interact with it well. So it becomes a bigger length in a more compact area. And there it is. This was the graph that you see here. I like to usually draw it like this. I'm sorry, my drawing's bad. I like to prefer to think of it this way. This is the magnetic portion because up and down makes more sense to me personally. I don't know why. This doesn't make sense to me that much. I mean, this is not actually what's happening. It's just a graph representation, obviously. But this is the imagine this almost, again, not the same thing as a magnet moving up, creating a current here. So this is the electrical field here, which is how we wanted. Peak here, peak here. Sorry, I kind of drew it poorly, but you get the gist. And here, this is a magnetic wave, which causes this. So that's the difference, is the type of standing waves are different a little bit. And what we draw here is a magnetic wave, not electrical wave. And this was the key for me to understand why it's half a wavelength and how it resonates at this wavelength. So another warning is that remember that there are antennas that are so small relative to a giant wavelength, right? Why is that? Well, it's pretty simple. A, antennas are three-dimensional objects, and B, there are different modes of oscillation, as I mentioned. There's there's other modes. It could be quarter of a wavelength. They do look different, and so they need to be designed different. But there's like antennas that look like this, blah, blah, blah. Remember that these are A, working with different modes of oscillation, or resonance, and B, these are like, I think, maybe something like, when you see a chip antenna, don't just think of it as like a wire inside. It could be. I'm not super sure on this. Please don't quote me on this. It could be something like this. You know what I'm saying? So yeah, this was just the very basics. I'm not a physicist. This could be just plain BS for all I care, but I asked the physicist and the explanation they gave me was so intuitive. It took them 2 seconds to make just click. It was like, oh, the internet explanations were so terrible. Now that you explain it to me this way, it just instantly clicks. And it's so intuitive. So this was just the explanation I got because I was very confused, especially because people just kept talking about the mode 1 like this, right? It was like, this isn't this. Like, how is this helping? It's because of this. I actually hope this was helpful, and I'm sorry I'm not very good at talking. I kind of mumble a bit, so I hope this was actually helpful, and I hope you like this video.